In this lecture, we will talk a little bit about correlation and what is it and how to use it. So, first question is how to guess the future, right? So, it's hard to guess the future because usually we have no complete information. So, what we typically want to do is that we get some partial data about something and we want to figure out what the outcome is. Like we had at the very beginning of the course, the hour of studied and the grade on the exam, or if we observe some animal attributes, we would like to know if the animal is warm-blooded or cold-blooded. Right? So what's the prediction? How does it work? So you look at other subjects or individuals that are somewhat similar to the thing you are trying to predict. You look at the outcomes, what happened there, and then based on those you try to guess what will happen with the subject you are trying to look at. Right? So I guess I know how long it took for people to study and what grades they did, and then I try to, based on that, guess if somebody studies X hours, what grade they will get. Right? So it's based on historical data. You have historical data, and from historical data you are trying to predict something that will happen to new partial data. This lecture we will look at variables that have numerical values. Let's start with two variables. You have some, let's say, x, variable x, and y that depends on x maybe. You would like to hope or find out if that depends. So you can try to see if there is any trend, right? If there is a positive association such that if x is increasing, then y is also increasing, or if there is a negative association such that if x is increasing, y is decreasing. Right? Positive association example for if we study longer, then we get a better grade. Right? Or maybe there is some pattern. Right? So if you look at the data and plot x and y in 2D, maybe you will get some shape of the dots. Right? You do scatter plot and maybe it will show that there is some pattern that the dots create. Right? If there is some pattern, life is always good. Right? And the pattern can be linear, which means that you can write y as a constant times x plus maybe some offset, right? Or it can be non-linear. It can create some funny shapes, and then you have to look at it to figure out. So good practice is first you look at the data, try to visualize them, and then you try to figure out if they have a linear or non-linear relation, or if there is a positive or negative association. So good practice, always try to look at the data, because sometimes if you do the math it can give you a number, but it may be misleading. Variables: x, daily temperature, and y, the number of lemonade sold. This is example of two numerical things, right, from our favorite lemonade sales. Right. The question is, are x and y associated somehow, or we'll call it correlated? And if so, how? Our question is we want to try. And what you do is you do a scatter plot first. In the scatter plot you may see if there are any trends, like things go up, down together, right? And you can see if one of the variables as it changes, if the other one is changes. And here what you do, you look at the x-axis is the daily temperature, and the y-axis is the number of lemonade sold, and you can try to see if it increases, decreases, or neither of those things happen. And then there is a second question: can you draw a linear line through the data? So if you have the data plotted, can you draw a line that goes through the data? And if yes, then you will get linear association. And sometimes you cannot draw a line, but maybe you can draw some other polynomial, and then you will say you have a non-linear association. Right? And sometimes you get just cloud of points, and then you don't have association. Here's a correlation. You can think of correlation of a measure how well your data fits is a linear function. Right? Here are some examples. So for correlation, it will always have value between 1 and -1. If it has 1, that means that the data nicely fit a line, and the line is increasing. So as x is increasing, y is increasing. If you have -1, then it means that the data also fit a line, but this time the line is decreasing. So if x is increasing, the y is decreasing. And then as the number gets closer to 0, the data looks less and less like a line and more like a cloud of points. Right? So if you look at the correlation 0.8, it still looks somewhat like a line, but the points are a little bit more scattered around the line. Around 0, it's getting more like a cloud, but it still looks like an ellipse maybe that is tilted upwards. And if you look at the correlation 0, it's just a cloud of random points. There is no trend that you can observe. Okay? What's somewhat misleading sometimes, that even if you have a little bit of data that is a little bit off, and then you will get a correlation that is not 0. But that doesn't mean that there really is any. Right? So getting exactly 0 is very hard. Right? But if it is sufficiently away from 0, then it becomes interesting. What is important to notice is that 1 means that the data behaves like a line that is increasing, and -1 that is decreasing. It doesn't say what's the slope of the line, right? So the line can be going steeply up or not so steeply up, and you will still get correlation 1. On the other hand, if you have correlation 0, it doesn't mean that there is no relation between the points, between the values. Right? You can see examples where correlation is 0, but there is no line that fits the data well. Right? But obviously there is some relation between the data. It's not just random cloud of points. Still, you can have correlation 0, just because the relation is not linear. This is one of the reasons why it's important to try to look at the data, and if you get that the correlation is 0, it doesn't mean that the data are having no relation to each other. You may ask, if you have correlation, some number, what is high and what is low, right? So it's there is no like natural number or natural cutoffs that one can come up with, but reasonable is that if the number is close to 1, it is strong association. If it's close to 0, it is no association. For example, here we have a suggestion that maybe if you have correlation coefficient in absolute value at least 1/2, then you say that it's strong. Between 0.3 and 1/2 it's moderate. From 0.1 to 0.3 is weak, and around 0 it is none or very weak. Right? You can kind of see it on the line where at different thresholds of the R values you have example how the points look like. Okay? There are other interpretations where you can try to say, oh, between 1 and 0.8 it's very strong, and between 0.6 and 0.8 it's strong, and 0.4 to 6 is moderate, and 0.2 to 0.4 weak, and between 0 and 0.2 very weak or none. But it's different people have different ways how to describe it, but in general, closer to 1, stronger association, closer to 0, weaker. Okay? Also closer to -1, stronger. We have to look at the absolute value. So finally, how to calculate the correlation. So here it is. I have a bunch of data, and there is I index them by I, and for each data point I have xi and yi, two coordinates, right? All right. So if I want to calculate the correlation coefficient, first we calculate the means. So x bar is the mean of all the x values, so it's average, sum of xi over n. Same for the y bar is sum of yi over n. Right, and now how does the formula look like? So in the numerator, you take the xi minus x bar, which means how far is the value of x from the mean, times how far is the corresponding yi from the mean, right? So that's in the numerator. And what's in the denominator? In the denominator there is square root of and now you take product of two things. You take all the differences from x to the mean squared, sum them up, and multiply it with all the differences between yi and the mean of y squared, and sum these up. And then you take square root. Right, so maybe this is a little bit difficult to remember or see what's going on. So, but what's going on is that you are trying to scale the differences in x and the differences in y somehow to some standard units. Right? We will see on the next slide how the calculation goes. What's important is you can try to look. So what happens if xi is equal yi for all I, right? So if they are always the same, right? So if xi is equal yi, then the means are also the same. Then the mean of xi is the mean of yi's, right? So in the denominator, you will get xi minus the mean of x squared, and the whole thing will be squared. So the both of the sums that are in the denominator will be same. So if you take a square root, you will only have one of those sums, and it will be sum y equals 1 to n xi minus xi, the whole thing squared. And in the numerator, you will get exactly the same sum as well. Right? So you will get coefficient 1. You can try it with particular numbers if you wish. Right. So here's the scaling. Right. So if I have a variable x, then here is how it looks in standard units. Right. So I take xi, subtract it from the average of x, the mean of x. I recall how the mean looks like, and I divide it by s, which is the standard deviation. Right? In standard deviation, here I have the square of standard deviation 1 over n times sum I from 1 to n, and the differences of xi's from the mean squared. Right? And these are very similar to the thing you saw on the previous slide. Right? In the numerator, you saw the kind of sum of x's, but there was the s was missing. In the denominator, there were the s's there. Right? or the square root to get the standard units. So here is again how one can do it. So you have y in standard units and x in standard units, and you take a product of these two and then take the average. You could think of it that the right to see measures how clustered and scattered around standard deviation. So here is the formula: the average of product of x in standard units and y in standard units. We can try to look back at the slide before, that the x minus xi is the first part of the product, and then y minus yi is the part of the second product, y in standard units, and the denominator moves things to the standard units. And because then the denominator there is a division by n, and here you have the product that you take the average, then you also divide by n, and the n's cancel. So anyway, you can also think of correlation coefficient of average of product of x in standard units and y in standard units. Okay? So maybe it's easier to remember. In Excel, it's fairly easy. If you want to calculate a correlation, you say what are the two things where you want to calculate. You have to say what is the xi, what is the yi, and it will do the formula for you. Right? Very lovely. And here is our favorite data set. If I want to calculate the correlation, correl, and maybe we can do between oranges and temperature. That's it. So the correlation is 0.434. In pandas, calculating the correlation coefficient is fairly easy. If you have things in data frame, you call the function CORR, and it will calculate for you correlation of every pair of variables. You can get a nice table. It's index 1, 2, 3, 4, 6, 7, 8, 9. These are different columns. Right? We created in this example 10 different columns, and each of them has 10 entries. And then for every pair of columns, you can try to calculate the correlation, and this will calculate the correlation by just calling df.core. A bonus, you can also display it with this nice table that the color somehow corresponds to how large the correlation is. Let's try to do some entertainment with correlation with Python. So here we import pandas, seaborn, numpy, matplotlib, just to make everything ready. So this first question, make a random data. So I will first fix a random state, np, so the numpy, random state, and here you start with random seed. Okay, this will be useful for making the result reproducible. So I will create maybe I must first list rs rand 10 10. So now I will get an array 10 by 10 that has random numbers in it, and if I run it again and again, the array is still the same. If you change the seed, the array will be different, but if you run it and have the same seed as me, you should get the same array. Right? Now we create a data frame from it. data frame. Tada! So you have 10 columns, 10 rows, and here are the random numbers in it. Right, I should maybe call it something, df. Now if I want to calculate the correlation, I will like df.cor. And now what it did, maybe misleading, that now it took the 10 columns that it had and the 10 columns again, and now this was always the x and y, and calculate the correlation between the two. So you have always one on the diagonal because you are having the same variable against itself, and you have some other numbers that are of diagonal. Okay, or I will make a copy of it, and if you just put core, it will draw it. You can make it a little nicer, styled background gradient. If you put background gradient, now it will make it such that you see it darker when the number is larger in absolute value. Okay? So numbers, actually here the numbers, when they are larger, it's darker. The negatives one are white, maybe that's not the best. Right? CMap cool worm. Oh, maybe I will spell it once. Okay. And now the larger it is, it gets more red. The smaller it is, it gets more blue. So now kind of easy to see the ones that are negative, high negative, and easy to see those that are high positive. 0.4, this is high negative. Okay. And sometimes if you have too many digits, you can also format just to is the table a little bit smaller, maybe easier to see, because the data is random. No matter how the data look like, the numbers should be one on the diagonal, and then here positive correlation between these is negative. You can see that the real close to 0 is not that often. So even if you have random data, the correlation between them can be quite large. Here we have the example that we have data set that each of these 10 columns have 10 entries, and you can see that the correlation is sometimes quite large in absolute value at least. Right? So what is the problem is that we don't have enough entries, and if there is not enough entries, you can get high correlation even for random data. But if the number of entries we have is bigger, maybe I will comment this out. So now the data frame has more rows, then the correlation is getting smaller. Still some of the rows may have high, but most of the time the absolute value is getting down. If you have 100 random numbers, it's even closer to 0, 1000. Almost no correlation among them. So it should also be an example that if you don't have enough data, you may get a correlation even if perhaps one would not expect one. Pair plot. And this pair plot is a great feature because it's the pair plot you can kind of get a guess what the correlation should be, and you can make a educated guess. So if you have Seaborn, then you can load the dataset iris and create the pair plot. If you have the pair plot, you can see if you can guess how the line is sloped up or down and how closely the data resemble the line, and see if you can guess how the correlation will look like. Right, let's try to look at the correlation of the iris dataset. So we can load it from SNS, load dataset, iris, bam, right? So you have the sepal line, sepal weight, petal line, petal weight species. I'll save the data frame, and now we can do a pair plot. So pair plot data frame. Wait a little, and here you have the scatter plots for all of them, and if you write here kind equals rec, then you will also get a line that approximates the points. And now this should give you a hint how the correlation should look like. So this line is going down, so maybe the correlation will be negative, but it will be close to 0 because this is a bunch of random points. This line is increasing, so it will be positive, but it will be maybe closer to 1, because the points look like they are following the line, and same as this one, right? One slightly negative, this negative, these are negative, positive, negative, positive. This will be very high, it's almost a line. This not as much line. So let's see. So df.core. Maybe I should forget about this form. When the thing is complaining, you cannot convert string to float. It's because if you remember how the data frame looks like, it has this column species that is not numerical, so we cannot calculate with it. So what you could do is write here numeric only, and now it will work just fine, right? So now we have the correlation, and we can style background gradient. What did I mess up? That's okay, good. About now, right? So the dark are the high ones, right? And you can plot the pair plot, and now you will see both of these things. And negative close to 0, positive closer to 1. This one is the very high, close to 1. Should be this one. Okay? If you really want to draw the pair plot here, maybe one should use also color for the species. See if it will work, but then it will not be as obvious with the lines, right? So we didn't color the species because then the lines are easier to see and correspond to the correlation. So I'm comment it out. This is the final picture. Right, let's try to eyeball data and see what the R value is. What's the correlation? So if you see data that look like points that are on a line and the line is decreasing, then the value will be -1 or close to -1. Right? And it doesn't matter how big is the slope. As long as it is decreasing, it will be -1. If it is increasing the line, slope is increasing, then r will be 1 or close to 1. Right? The closer it's to the line, the closer to is 1. And if the data are like bunch of ball of points and it's not quite clear which way to draw a line that looks like the data, then it's probably close to 0. So just by looking in the data, you may have a guess which of them have positive or negative correlation and which may have higher R or lower R. Here's a little guessing game, which pair of the two plots has higher value of R. Okay? So in A, the first one looks like a cloud of points, maybe the correlation will be close to 0. The right one looks much more like a line, and it's in a positive direction, so it will be a positive number. In B, the line goes down, and the points on the left resemble line much more than the points on the right. So the points on the left will have number that is much closer to -1 than the points on the right. When it comes to C and D, it's harder to tell. For C, the correlation will be positive, and on the left it looks like the numbers are a little bit more in a cloud, but on the right there are several outliers which may ruin the number. And similar for the D, it looks like the line may be going down, but there are outliers that may ruin the number. Right? So at D it's perhaps negative, at C it's perhaps positive, but which one of them is closer to 1 in absolute value, at one would have to actually calculate it. Here is the pop quiz. You have some scatter plots A, B, C, D, and what you should try to do is figure out which of these R values belong to which picture. Right? So what are the guesses? Okay? So we have values, some of them are rather big positive, and then there are some that are kind of small. Right? We should try to think about it a little bit. Right? So which of them should be the big positive? Right? So which of them looks more like a line that's increasing? Maybe B looks most like a line that's increasing. Right? Then there is a second line that is increasing, but not as much. It looks like maybe D could be seen as a line that's increasing, but it's a little bit more like a cloud of points, so it would be the smaller one. Then there is a decreasing one, that is the minus 0.72. That is perhaps the plot A. And then the plot C, it looks like a bunch of points, and it's not quite clear how to put line in it. So maybe that's the one that is minus 0.02. Pitfalls of correlation analysis. So if you just look at the number, you may miss things. You can maybe imagine easily that if the relationship between x and y is not linear, then you may have correlation that's close to 0, but there is a pattern to be seen and used. And we saw pictures like that on previous slides. If you have data with few outliers, the outliers can influence the results a lot. So it may be good to see if there is like few points that are off, but that they are ruining the whole result. Okay? And then last thing, if you have small sample size, then you may have unreliable results. But that's not just for correlation, that's in general. If you have few samples, then doing some data analysis with them is hard. The more samples, the better. Okay? Correlation and covariance are covered by StatQuest. Great videos, highly recommend. Those are my favorite. And here is a little bit more reading materials that you can use to learn more about correlation coefficients.